welcome back. This is lesson 8.3, and yes, we're doing more tests to figure out if series converge or diverge. In this lesson, I'll introduce to you two new tests, one called the direct comparison test, and the other one called the limit comparison test. Now, I think the direct comparison test is pretty self-explanatory, straightforward actually. Here what I'm saying is, if you've got terms in a series a sub n, they're positive, okay, and then you're going to compare it to another series, b sub n. Notice I'm saying the a values are always less than or equal to the b values, okay. Well, if the series with the b values converge, then the series with the a values also converge. In number 2, if the series in A, that's the smaller numbers, diverge, then the larger one must also diverge. And I think that's quite intuitive. Really informally, number 1 states this: if the larger series, that's of course in this case b sub n, converges, then the smaller series, which is the original one, a sub n, must also converge. Whereas in number 2 here, statement number 2, what I'm saying to you is if the smaller series, that's a sub n, diverges, then the larger series, b sub n, must also diverge. So really what you're trying to do here is pick a series that is very similar to the one you have, either a little bit bigger or a little bit smaller. Make sure that it's bigger for all the values or smaller than all the values, and then do a quick test on that alternate series, and from there decide if it converges or diverges based on either number 1 or number 2 in the test above here. So number 1 or number 2. Okay, so let's take a look at example number 1 and we can solidify this idea. Here we have the sum of a series from n equals to 1 to infinity of 1 over 1 plus 2 to the power n. That's a difficult series to actually do. But if we were to compare it to something, what could we compare it to? You might be thinking, let's compare it to something very similar, like the sum of n equals to 1 to infinity of 1 over 2 to the power of n. Okay. Why would I compare it to that? Well, that's a nice series because this is really just a geometric series. And I know that since the r value, the common ratio, is 1/2, that of course is less than 1. So by the geometric series test, I know that this converges. Now that's nice. The comparison one converges. But now the question I have for you is, how do the terms of 1 over 1 plus 2n compare with the terms of 1 over 2 to the power n? Are the terms on the left bigger or smaller than the ones on the right? Well, I hope you can see that the denominator is, of course, bigger. But if I take the reciprocals of these things, then a bigger denominator actually represents a smaller value. So therefore, you should see that this is less than or equal to. And that's interesting then, because what you just said to me is the following. Since the sum of 1 over 2 to the n converges, so by the geo series test, and you just told me that 1 over 1 plus 2 to the n is less than 1 over 2 to the n, so think of the lesser one as your a sub n, think of the bigger one as the larger b sub n, then what you can say is then I know that the sum of 1 over 1 plus 2 to the n must also converge. And why? Because the direct comparison test says so. Okay? And that's how we use this direct comparison test. All right. So the second one and the third are very similar. You have to find the sum that's very similar to that, a little bit simpler. And so for number 2, if you can think about comparing it to 1 over n, I would be glad, because that's what I would do. The sum of 1 over n, that's a p series where it's equal to 1, or really this is called the harmonic series. So whatever you want to say, I'll just say by the p series test. Since p equals to 1, this diverges. Okay? Now, because it diverges, once again, I'm going to ask you to compare 1 over n minus 2 with 1 over n. 1 over n minus 2. Well, if I compare the denominators, of course, n minus 2 is smaller. But when I do the reciprocals, we flip it. So, of course, the term on the left is bigger. And that's interesting because my comparison term diverged. That was the smaller series. The one I'm looking for here is the larger series. So once again, I can write that whole blurb again, but I'm just going to simplify this. I'll say because the 1 over n minus 2 is bigger than, I know that the sum of 1 over n minus 2, also must diverge by the direct comparison test. So I simplified the wording a little bit. The wording for number 1 in blue here is much, much better and more accurate, but I'm just trying to be efficient with my time and your time. Okay? All right. How about the third one? You have to decide what you want to compare it to. If you are thinking compare to the sum of 1 over root n, I would naturally think the same way. The p-value in this case is equal to 1/2, so it's less than 1. So by the p series test, once again I'm naming it, right? This must diverge. Okay. And then once again now, let's compare the root n plus 1 with 1 over root n. This must be bigger than that since it's plus 1. The reciprocal means it must be then less. So notice in this case what I've said to you is the larger series. This is the larger one, right? Larger diverges. So what do we know about the smaller? If the larger diverges, the smaller it must be, and I'm looking back here, and I don't see anything that says anything about the larger being divergent. So guess what? This is a dead end. It doesn't tell us anything. So do we just say it's inconclusive? I say, So our mistake here was trying to figure out this, and it was less than. I want you to go back and try now to compare it with something else. So compare it with something else similar, and maybe you would like to try 1 over n. We know this is a p series. We just did this in example number 2, right? Where p equals to 1, therefore it diverges. And so now let's compare 1 over root n plus 1 with 1 over n. And I hope you see that in this case the term on the left is less. Sorry, not less. Is more, right? Because root n plus 1 is always less than n, so the reciprocal must be more. Since now this is the smaller series, and it diverges, then by the direct comparison test, I know that the larger series must also diverge. Okay, there you have it. The direct comparison test done. Now, how about this thing called the limit comparison test? So, the limit comparison test says the following. If you've got terms of a series that are always positive, and another series that also its terms are always positive, and if you take the limit comparing the two as a ratio, and that limit equals L a number, that's of course finite and positive, then both the A sub n series and the B sub n series converge, or they both diverge. So you're like, when would we use the limit comparison test then? Well, we use it when we try to compare messy algebraic series to an easier series, like a P series. Okay? And the idea here is to please choose a P series that disregards all but the highest powers of n in the numerator and the denominator. It's like doing the n behavior model when I take the limit. Okay? So let's take a look at 3 examples here to solidify your concept of the limit comparison test. And once I've done these 3, you're ready to try some examples of your own. Or not examples, some assignment questions of your own. So once again, you want to compare. So I have 1 over 3n squared minus 4. You're looking at the highest powers of n. So I would probably compare this to 1 on the top and just n squared on the bottom. We know this sum, by the way, is a P series with P equals to 2. So therefore, by the P series test, we know that this must converge since it's bigger than 1. So knowing that, let's now apply the limit comparison test and take the limit of n approaches to infinity of our original series, 1 over 3n squared minus 4. That's our A sub n. And let's divide this by our b, the one we chose to compare it to. This, of course, written nicer, is just the limit of n approach to infinity. 1 over 3n squared minus 4 times n squared over 1. And by the comparison test with the n behavior model, I can now say that we're just comparing n squared with 3n squared, and that gives us 1/3. Notice this is a value of L, right? A number that is finite and positive. So because I know that, since B sub n converged, therefore I'll say the following. So once again, I'll be wordy here. So since the limit of n approach to infinity of the comparison A sub n over B sub n is finite and positive, and the summation of 1 over n squared converges, then by the limit comparison test, I'm going to use LCT for that, the limit comparison test, the sum of 1 over 3n squared minus 4 must also converge. Alright? So once again, I was a little bit more wordy here. That's what you should do on your AP exam. But for all the rest of these, I'll just try to cut it short. Alright, let me show you number 5, and then maybe I can get you to attempt number 6 on your own. Once again, what are you going to compare this to? Is root n on the top and n on the bottom. That simplifies probably to the sum of 1 over root n. Once again, in this case, this is a P series with n equals to 1/2. So then by the p-series test, we know this must diverge. Okay, so let's take the limit now. Take the limit as n approaches to infinity. Root n over n plus 7 divided by 1 over root n. That, of course, if you want to skip a step and write it nicer, is just timesing by root n over 1. Root n times root n is just n, so this is the limit as n approaches to infinity, of n over n plus 7. By the n behavior model, I believe you get the answer of equaling 1. 1 must be finite. 1 is also positive, so that's great. And therefore, I'll say then, by the limit comparison test, since our comparison function diverges, then our original function must also diverge. Okay, I think I've given you enough examples. I'm going to ask you to try number 6 on your own. Once again, don't cheat and just copy my answer. Please try this yourself first and then come back and check. Alright, I leave the rest to you. See you in class. N cubed, that simplifies to 1 over n squared. P series with, this was not n, it's p, right? P equals to 2. So by the p series test, we know this converges. Hello, limit comparison. So I'll take our original. I'm going to skip a step this time. We'll just, instead of dividing by our comparison, multiplying by its reciprocal. That means I get n cubed over n cubed with the n behavior model. N cubed over 4n cubed, I should say. And that equals to 1/4. Yay! Finite! Yay! Positive! Yay! By the limit comparison test, the sum of n equals to 1 to infinity of n over 4n cubed plus n squared plus 5 must also converge. Woo! Now you're ready to do some questions on your own.